Hi everyone and welcome on board your really long-haul flight. On this channel we've put together a compilation of some of the most jaw-dropping moments from the sky, so now all that you need to do is find a comfortable place to sit, bring out your favorite drink, sit back and relax. Chaos. A brand new airliner, the most recent and advanced version of an old trusted type, rendered almost completely uncontrollable just minutes after takeoff. Now, you might think you know this story, but trust me, you will be surprised. Stay tuned. Sometimes a story is so big and includes such unimaginable monetary interests that skewed narratives are consciously being introduced in order to change the public's opinion about what actually happened. And this is such a story. And because of that, over the next hour or so, I will take you through some really complex explanations. But stay with me, it will be worth it, I promise. Money. The one thing that all businesses strive for, and the foundation of what makes a capitalistic society run. This is true for airlines and aircraft manufacturers alike, and that's what ultimately drove Boeing to create the 737 MAX model, the latest iteration of their hugely popular narrow-body jet and the foundation of the company's financial success. But what I need you to understand here is that the MAX was actually never really supposed to exist. In the early 2010s, the 737 was already an aging design, harking back to the 1960s, and Boeing was planning for a modern successor. An aircraft that would have taken the full use of all modern technology available and therefore make it much more fuel efficient for the airlines. But then Airbus came into the picture and decided to strap new engines onto their Airbus A320 family, calling it the Neo series, improving its efficiency with as much as 16%. Now Boeing knew that creating a brand new aircraft would take them around 10 years to do, and if they did that, their 737NG family would not be able to compete with the Neo, thus leaving a potentially huge amount of money on the table. So they quickly scrapped their new aircraft and instead started looking into the possibilities of equipping the old 737 with the latest, most efficient CFM LEAP engines. If they could do that, they would not only be able to match the Neo family in terms of efficiency, but it would also be able to be flown by the same pilots as the old 737s were. That was providing that the flight characteristics of this new variant didn't differ from the old 737. Remember that. Now the airlines loved this idea since it promised increasing yields, money, as well as an improved environmental footprint. And one of the first airlines to buy this new 737 MAX model was Lion Mentari Airlines in Indonesia, more commonly known as Lion Air. It was the largest airline in Indonesia, and earlier it had struggled with a slightly checkered safety record, failing to be included in the International Air Transport Association, IATA, back in 2011 because of safety concerns, and it was also banned in all EU airspace up until 2016. But after that they improved a lot, and in June of 2018 they received a positive safety rating following an audit by the International Civil Aviation Organization, ICAO. At the same time this story takes place, in October of 2018, their fleet consisted of several different aircraft types, and importantly for this story, 11 brand new Boeing 737 MAX 8s. The aircraft that we will be focusing on today had registration Papa Kilo Lima Quebec Papa and had received its airworthiness certificate only 2 months before this flight. And those had not been 2 problem-free months. For example, in the beginning of October, several problems with the aircraft's air data inertial reference unit had been recorded, including a maintenance fault message indicating an angle of attack signal out of range on its left-hand side. This was also combined with several electrical issues, but all of those snags were rectified on the 9th of October according to the aircraft's technical log. Now, I will soon be referring to several technical systems here, so it's probably good to do a little bit of a systems review before we continue. In order to display useful information on the pilot's instruments like speed, altitude, attitude and heading, loads of different information has to be collected, processed and then converted into electronic signals. On the 737, this is handled through two main computers known as Air Data Inertial Reference Units, one for each pilot. Those ADIRUs take information from our laser gyros in the inertial reference system, as well as a multitude of probes and sensors on the outside of the aircraft. Those sensors include pitot-probes who measure the dynamic pressure, speed, the static ports who measure static pressure, altitude, and angle of attack sensors who are these wing-looking vanes that measure the angle of the air hitting the aircraft and wings. Knowing the aircraft's angle of attack is crucial for calculating if the aircraft is close to stalling, meaning that the wings will be stopping to be able to create lift, but also for readjusting the values of the other probes, since the air hitting them differently can cause changes in their readings. Anyway, all of those probe values are then combined in two air data modules and then sent into the ADIRU, where it's prepared and then presented to the pilots. Now, some probes produce separate signals for the standby instruments, but that's not really important for this story. What is important, however, is understanding that one of the tasks handled by the ADIRU is to sense if any of these inputs are faulty, and in that case present a failure flag or disagree warnings to the pilots to alert them about what's going on. If, for example, the two ADIRUs senses a difference in altitude, going above a certain value for a certain time, well, then we will get an altitude disagree warning. And the same goes for both the speed and, in theory at least, the angles of attack. So, why am I saying in theory then? Well, it turns out that the angle of attack disagree was a warning that all Boeing 737NGs had and all the 737 MAXs also should have had. But in the case of the MAX, the software designers had rewritten the code for it, attaching it to the presence of an angle of attack indicator on the pilot's displays. But that indicator was an optional extra, which the airlines had to pay for including, and since very few had done that, including Lion Air, that angle of attack disagree warning now wasn't available on this aircraft. Neither the FAA or Boeing had initially noticed this during certification, but when they did, Boeing considered it a minor issue, which they plan to fix in a later software upgrade. Before we get to the flight, there is also another system that I want to discuss, and that's the pitch trim system. On the 737, the horizontal stabilizer in the back can be moved in order to affect the pitch of the aircraft. The elevators at the very back are the primary control surfaces, but the whole stabilizer can be moved in order to keep the aircraft balanced as its weight shifts or the speed or configuration changes during flight. We pilots control this with the help of an electric trim switch on our yoke, and when we move those, we can see that the trim wheels move on both sides of the throttle quadrant. Now, inside of those wheels, we also have a trim scale, which shows us the setting of the stabilizer. And that's super important for takeoff in order to make sure that the aircraft doesn't start pitching up too early or becomes too heavy to rotate. During the flight, when we are flying manually, it's also super important to keep updating this trim setting to avoid having to push or to pull too much on the controls. The stabilizer is a huge surface, so it can exert a lot of pitching force if it's not handled properly. And that brings us back to the aircraft in this story and the troubles that it had experienced. That angle of attack signal out of range message that I mentioned before was a clue that there might be something fishy with the left angle of attack vane. But the problem disappeared once the associated computer was reset and the aircraft was then just released back to service again. Then, on the 26th of October, 3 days before the accident flight, the aircraft arrived into Manado Airport after a flight from Tianjin in China. After landing, the pilots reported that they had received both altitude and speed flags on the captain's side during the flight, and on top of that, there was also an illuminated maintenance light on the overhead panel. The engineer on duty in Manado checked the fault information in the aircraft's onboard maintenance function, OMF, which showed some type of issues with the stall management yaw damper computer. But when the computer was asked to do a self-test, the problem just cleared and the speed and altitude information came back again. So with that done, the aircraft was just released back to the line, but already on the following day, when the aircraft then flew from Manado to Denpasar, the same issues reappeared. Now the new engineer, this time at Denpasar, went through the same procedure, which again seemed to solve the issue. And before you start slapping your forehead here, this was the described maintenance procedure to follow when faced with this particular fault. Even though a repetition like this should have raised some warning flags. But the aircraft was once again released back to service, and for the following 2 flights the problem actually didn't reappear again. But when the aircraft had to do the 4th flight of the day, from Denpasar to Manado, both of the speed and altitude flags reappeared again, now together with the speed trim fail and Mach trim fail warning. What had actually happened here was that a coil inside of the left angle of attack vane had a damage on it, and that damage disrupted the signals from the vane whenever the temperature outside became too cold. Those 2 middle flights had been reasonably short and flown at the lower altitudes where the temperature had been reasonably high, which was why the fault had not reappeared there. But on this much longer leg, the fault again activated. Like I mentioned before, the angle of attack vane was supposed to feed corrections to the signals from both the pitot and static port, and since those signals were now disrupted or completely inaccurate, it meant that those corrections were also inaccurate, which triggered those flags, as well as all of the other faults. In any way, the engineer in Manado had no idea about this damaged coil, so he instead now got to work checking through all of the numerous fault messages that the aircraft's internal log had created. And if you think that multiple similar faults like this should raise some kind of internal alarm for the maintenance organization, you are absolutely correct. But in this case, the contractor that Lion Air used for their maintenance had a slightly different way of defining reoccurring faults, so it wasn't properly highlighted. During the night, the engineer did several tests and resets, but because it was raining, he couldn't do some of them due to the lightning hazard. But he did find ways to work around that, so when the flight crew, the same ones who had flown the previous flight, came back to the aircraft in the morning, it had once again been released to service. The pilots discussed the actions that had been taken by the engineer, but they weren't really happy with what they heard. They thought that more should be done to fix this, obviously reoccurring issue, but the engineer told them that this could be better done at their destination, Denpasar. Now this was not great, as it shows that the engineer probably knew that there were still something wrong with the aircraft and allowed it to depart anyway, but that wasn't the worst part here. Because on the next flight, the crew did indeed experience the same faults again, as well as an auto-throttle failure during the takeoff roll, and when the fault codes were downloaded from that flight, it looked like the problems had reappeared immediately after engine start, meaning that the crew likely had elected to dispatch with the flags on the captain's side already present. If that was the case, it was a major breach of dispatch requirements, since we should never leave the airport with faults like this. Anyway, the flight was eventually completed safely to Denpasar, and when the aircraft arrived, still with these same problems, the engineering team decided to finally replace that left angle of attack vane. A good decision, but now a truly incredible coincidence happened. Because since the engineers didn't have any spare angle of attack vanes in their stores, they had to order a new one, and when that new one arrived, it turns out that it wasn't new at all. Instead, it was a refurbished one that had been fixed up and recalibrated by an American company called Extra Aerospace. It later turned out that they had used a calibration tool, different from the one recommended, but still allowed. The only problem was that this tool included a setting that, if activated by mistake, could allow a calibration to go through with the vane outputting the wrong signals. In this case, the vane worked perfectly, but with the small caveat that it was showing a 21-degree higher value than it should. Now, as part of fitting this new vane, the engineers should have run the new vane through a set of tests to verify its indications, which should have caught this, but there was no records of this test ever being made, and when the engineer in charge was asked for it, he showed pictures from the cockpit of a different aircraft. So that sets the scene for Lion Air Flight 043, the flight before the accident flight, and here is where this story becomes almost unbelievable. But first, if you know almost anything about this accident, you will have noticed that so far I haven't mentioned a system known as the Maneuvering Characteristics Augmentation System, or MCAS. And that's because up until this point it had not yet entered the story. But now it will, and I don't think that there is a single aircraft system in history that has been as vilified and misunderstood as this MCAS system. So in order to set the record straight, I will now explain exactly what it is and what it was supposed to do. You see, when Boeing decided to re-engine their old 737s, they quickly ran up against a problem, one that their competitor Airbus didn't have. The wings on the 737 were too low to enable the bigger LEAP engines to fit properly below them without risking them striking the ground. Most of the efficiency gains from these new engines came from the much higher bypass ratio that these engines produced, which meant that making these engines smaller would defeat the whole purpose of them. So Boeing's engineers went to work and decided to place the engines further forward of the wing and also slightly higher up, which worked great, but then came the next problem. You see, in order for pilots who were rated to fly on the older Boeing 737NG to be able to also operate this newer variant without extra training, the aircraft had to both act and feel exactly like the older 737. But when the engineers modeled the MAX with these new engine placements, they saw that under very specific circumstances, more exactly during high angles of attack and with flaps up, these new huge engine nacelles actually started producing some lift, which acted upwards around the pitch axis, causing a slight pitch-up momentum. Now, from a handling point of view, this was not a problem. It didn't make the aircraft dangerous or unstable in any way, but it did mean that it wouldn't behave exactly like the old 737NG. In technical terms, the stick force gradient wasn't the same, which was a no-go from a certification perspective. So, what could Boeing do to solve this? Well, someone soon figured out that they had a similar solution for their KC-46 Alpha tankers, something known as the Maneuvering Characteristics Augmentation System. This was basically a software solution which worked through something known as the speed trim system to adjust the stabilizer pitch trim forward a bit when needed. The software could be programmed to only activate during those very specific circumstances when the aircraft was being hand-flown with high angles of attack and with flaps up, trimming forward when that lift effect from the nacelle started kicking in, and thereby basically simulate the same pitch feel as the old NG and also bring the stick force gradient back into regulation. This was a brilliant idea, since keeping the MAX within the same type rating as the old 737 without any simulator training requirement at all was a super important selling point for Boeing. Any extra training requirements in a simulator would mean extra costs and complications for the airline customers and therefore making it less competitive against the Airbus. Now, the idea was that this system should be a very rarely used function of the speed trim system. A system that was already being used in the older 737NGs, and Boeing therefore thought that the MCAS function didn't need any further explanation or even to be included in the manuals. And this is very important to understand for this story. You see, the speed trim system is something that 737 pilots are very used to. It kicks in automatically during certain circumstances when we are flying manually, and it's especially active after takeoff when the speed and configuration changes continuously. So the fact that the trim wheels would be moving by themselves was something that these pilots would be well used to. When Boeing were certifying MCAS, part of this included something known as a functional hazard evaluation, based on the level of risk that the system posed to the aircraft. Through several assumptions based on how pilots should react to a sudden erroneous activation of the system, together with how much the system would be allowed to trim, Boeing ended up classifying the MCAS risk as major on a scale that included minor, major, hazardous and catastrophic. And since major was on the lower end of that scale, it wasn't deemed necessary to further evaluate how such a failure might play out together with other failures. It was just tested in a simulator as an isolated fault to the original maximum trim authority of 0.6 degrees, used if activated at higher speeds and Mach numbers. Because of this, it was also deemed safe for MCAS to form part of the rest of the speed trim system, which only used one flight control computer at any given time, and therefore also only relied on one single angle of attack vane. During later testing, Boeing's test pilots found it to be necessary to extend the function of MCAS to include flights at lower speeds as well. And in that case, the trim function was expanded to 2.5 degrees of maximum trim, which is a substantially bigger trim movement. But that was not deemed as aerodynamically more hazardous than the previous limit of 0.6 degrees at a high speed and was therefore never tested. The FAA, who was in charge of overseeing this process, had delegated a lot of the oversight of these detailed certification tasks to certain approved Boeing employees. And it later turned out that all of the paperwork regarding this change in the authority of the MCAS system never actually reached the FAA. So Boeing knew about this system and what it could do, but never thought of it as a real problem. They assumed that a pilot who was faced with a potentially faulty MCAS activation would just take about 3 seconds to realize it, whilst counteracting it with elevator input, and then the pilots would use their electrical trim to cancel it and nothing worse would happen. They never took into account that a manual trim input would also reset the MCAS system, and if the high angle of attack condition was still sensed after that, well then MCAS would just wait 5 seconds and activate again, and again, and again. Like I said, this system was also thought of as so small and meaningless that Boeing hadn't even bothered to explain it in its pilot's technical manuals, so basically no one knew about it, especially not the normal pilots who were actually going to fly it. Now I should also mention that there was a way to stop MCAS and all other electrical trim movements, and that was by activating the stabilizer trim cutout switches as part of the runaway stabilizer memory items. But as we will soon see, that was not as obvious as it sounds. On the 28th of October 2018, the day before the accident, the 2 pilots who were scheduled to operate Lion Air Flight 043 arrived to the airport in Denpasar in the evening to start preparing for their flight over to Jakarta. They talked to the engineer, who informed them about the problems of the previous flight and that he had replaced the angle of attack sensor on the captain's side, which convinced the captain that the problem had now been solved. He then headed over to brief the cabin crew, and during that briefing he also stated that he would be pilot flying on the flight, and he mentioned again that there had been some previous technical difficulties with the aircraft. This is important because it shows that he was likely aware about the fact that there was a chance that something might happen on this flight as well, because you always have to be more vigilant after some major maintenance procedures have been done. During the briefing, the crew was also joined by a 3rd pilot who was working for one of the other airlines in the Lion Air group and who was also rated on the max, and he was invited to stay in the cockpit for the flight. They then walked out to watch the aircraft and eventually departed at time 22:20 local time after an almost 3-hour-long delay. And during the first couple of seconds after rotation, everything seemed to be working okay. But almost as soon as the landing gear had been retracted, a takeoff configuration warning sounded momentarily, which it definitely shouldn't. And then both the IS disagree and altitude disagree warnings appeared on the captain's side together with the stick shaker. Now, for anyone who hasn't been in a cockpit with a stick shaker activated, it's quite loud and definitely startling when you aren't expecting it. But this captain kept his cool and just pitched to 15 degrees nose up as he would normally, keeping the thrust in the takeoff setting. He then did a quick scan of the first officers and the standby instruments and concluded that his were the faulty ones, probably because he knew that the work had been done on his side. He therefore handed over the controls to the first officer, who had good indications, and then asked for the airspeed unreliable memory items to be performed. These consisted of disconnecting the automatics, turning off the flight directors, and then setting, in this case with the flaps were still extended, a 10 degrees pitch up attitude and 80% of thrust. That would ensure that the aircraft kept flying in a safe way whilst the rest of the checklist could be executed, and knowing those memory items by heart is therefore super important. At this time, the first officer was still hand-flying the aircraft, with the speed trim function activating a few times like it normally would. Interestingly, probably because the first officer saw how the speed was going up, he now also asked for the flaps to be retracted, and almost immediately when the flaps came up, he engaged the autopilot. Now, I should mention here that the memory item specifically instructed the pilot not to engage the autopilot, but this was likely done out of habit, and since it looked like the first officer had perfectly working instruments. For about a minute, the flight then progressed normally, with the captain looking for the correct QRH checklist to follow in order to deal with all of the different warnings that they had. And throughout all of this time, the stick shaker kept rattling away on the left-hand side. Then, the autopilot suddenly disconnected, and almost immediately the stabilizer trim started moving forward in a nose-down direction, but now with a much higher speed than it had been moving with before. Like I said, the crew would have been used to the trim wheels moving independently, but this time it wasn't helping them. Instead, it was making it much harder for the first officer to keep the nose up at the correct attitude. He therefore used his trim switch to trim up again, but 5 seconds later the trim just kept going forward, constantly a little bit more than the first officer trimmed back, making the controls just heavier and heavier. He tried to engage the autopilot again, but it immediately disconnected, and the trim battle then just continued. At this time, the captain called out a pan-pan, an urgency message to the controller, saying that they had instrument problems and asked to climb straight ahead. And when the controller started asking him questions, he just told him to stand by, a great way to reduce the workload. When the aircraft climbed through about 5,000 feet, and with the captain still working through the checklist, the jump seat pilot suddenly cried out, "You're descending!" The captain looked up and saw how a descent was indeed developing, so he told his first officer to keep climbing and just follow the flight directors. But this also made him look at what the first officer was doing, and he noticed that he seemed to be constantly fighting with the trim. The first officer now also said that the nose was starting to feel very heavy. I guess some of you might have already figured out what was going on here. The new angle of attack sensor had, like I mentioned, a bias of 21 degrees nose up, which means that as soon as the aircraft got airborne, the flight control computer on the left side noticed what it interpreted as a high angle of attack situation. Now, as long as the flaps were extended or the autopilot engaged, this only led to those other warnings: the airspeed and altitude disagree, master caution, and stick shaker. But as soon as the flaps were up and the aircraft was flown manually, MCAS had also activated and was now trying to replicate that stick force that we talked about before. The only problem was, of course, that the aircraft wasn't actually in a high angle of attack, so what MCAS now did was effectively forcing the nose of the aircraft down towards the ground instead. The pilots had no idea about this, since they didn't even know that this system existed, and whilst they were pitching up against it like Boeing had predicted, no one had thought of the fact that the system would reset and start trimming forward all over again every time that the pilot trimmed against it. When the captain noticed the reoccurring forward trim inputs, he soon figured out that they must be dealing with some kind of strange reaction by the speed trim system, and he therefore executed the memory items for a runway stabilizer, since he knew that this would stop the speed trim system. When he switched the stabilizer trim cutoff switches to cutoff, MCAS finally stopped, but this also meant that the autopilot would no longer be available, and they would need to trim manually for the rest of the flight. At this point, they were dealing with 3 different QRH checklists simultaneously: the altitude disagree, airspeed unreliable, and a runaway stabilizer. But all non-normal checklists are written with the assumption that no other faults exist, and none of these checklists included the phrase "land at the closest available airport." Because of that, when the crew now started discussing what to do, they decided to continue the flight towards their destination, Jakarta, an over 90 minutes long flight, since the weather along the route was expected to be fine. Now, just for clarification here, if you find yourself in a situation like this with 3 different checklists, 2 of which includes memory items and a continuous stick shaker, it is perfectly okay to return back and land, even if the checklist doesn't explicitly say so. I would even dare to say that that probably would be the best thing to do. Anyway, this crew just continued to climb, but they asked for a lower cruise level than normal, since they were not equipped for flight with reduced vertical separation minimum, RVSM, without an autopilot. And they also kept the passengers seated and briefed the cabin crew about the issue. When they started approaching Jakarta, the captain asked for an uninterrupted descent, and they kept their pan-pan, emergency status active until they finally landed safely on runway 25 left in Jakarta at time 02:56 local time. Now, very few sources have highlighted the importance of this flight in the reporting around this accident, but it actually holds some of the real keys to what was going to happen on the following day. First, it showed what a huge difference it made for the crew to be aware of the previous problems, since it clearly made them more alert. That's something you only get if you make sure that the technical log is thoroughly read through before the flight, or if you get briefed by an engineer, like in this case. Secondly, this was a very skilled crew where, except for maybe the decision to continue, the captain took all of the right decisions when they were needed. The extra crew member on the jump seat also quickly alerted the crew when MCAS started to force the flight into a descent, and overall the CRM, the crew resource management, seemed to be working reasonably well. So even with all of the mistakes that had made these problems possible, providing that these factors were in place, the MCAS issues seemed to be able to be contained. But unfortunately, here is where my praise for this crew will end. Because as they were now taxiing in towards their stand in Jakarta, they for some reason reset the stabilizer trim cutout switches. And as the passengers were disembarking, the captain did write up the problems in the technical logbook, but it didn't include the perceived stabilizer runaway, nor the stick shaker. Later, when he got into the crew room and filed his report about the flight, he wrote down the following description. Airspeed unreliable and altitude disagree shown after takeoff. Speed trim system also running to the wrong direction, suspected because of speed difference. Identified that captain instrument was unreliable and handed over control to the first officer. Continue, no normal checklist of airspeed unreliable and altitude disagree. Decide to continue flying to Charlie Golf Kilo at flight level 280. Landed safely on runway 25 left. As you can see, this didn't include the stick shaker, nor the fact that he had run through the runaway stabilizer checklist, and that in turn meant that the report wasn't given the priority it definitely needed, since it now just looked like an instrument problem. This lack of emphasis in the report on the truly dangerous part of the flight was later traced back to insufficient pilot training on how the Lion Air safety management system actually worked. Anyway, the problem was now that the same lack of information also hit the engineers who attended to the aircraft after the flight. When they opened up the technical log, they could just see that the captain had written up IS and altitude disagree flags shown after takeoff and a field differential pressure warning that had occurred later on during the flight. Now, it's worth noting here that all of these warnings and lights were the ones that were still present in the cockpit at the time when the captain wrote them down. If the angle of attack disagree flag would have also been present, it would likely also have been written down. But since Boeing had missed to include that on the Maxes without an angle of attack indicator, it now wasn't, so the failure was never recorded. The engineers now looked through the fault memory of the aircraft but didn't write down the reference codes. Instead, they mainly focused on the messages that the captain had written down. They then checked their fault isolation manuals based on this and followed its guidance, which caused them to just flush the pitot tubes and clean the electric connector to the elevator field computer. And since both of these systems were then tested and worked just fine, the aircraft was then released back to service, with the real fault still hidden and still very much active. This finally leads us to the accident flight, which would take place on the following day, early in the morning on the 29th of October 2018. It was still dark outside when the two pilots scheduled to operate Lion Air Flight 610 arrived to the airport in Jakarta. The first officer had not been originally rostered for this flight, but had been called off standby to do it at 4 o'clock in the morning. The route that they now had ahead of them was going to take them from Jakarta over to Pangkal Pinang, and there were 181 passengers booked, including 1 engineer plus 6 cabin crew and 2 pilots, taking the total amount of souls on board up to 189. The pilots went through the weather, NOTAMs and flight plans, and there seemed to be nothing out of the ordinary. The weather at both Jakarta and their destination was fine, and there was no real turbulence expected. So, after having checked everything, they walked over and briefed their cabin crew and then made their way out towards the aircraft. The captain was going to act as pilot flying for this first leg of the day, so when they reached the cockpit, he checked the technical log and then started setting up the aircraft, whilst the first officer went outside to check that their almost brand new Boeing 737 MAX 8 didn't have any kinks on it. Now, we don't know how much time the captain actually spent checking through the technical log, but when it came time to discuss the technical status of the aircraft with the first officer, he only mentioned that an ADF was unserviceable, nothing else. So it is pretty likely that he only looked at the back of the tech log where all the open technical items are kept and didn't look much further than that. And of course, the engineers had already fixed the problems from the previous flight, so those problems were not written up in there. If he had flipped a few pages back in the log, he would have seen the numerous write-ups that his colleagues had entered during the previous day, and then maybe this story would have had a completely different ending. But that sadly didn't happen. Like I mentioned earlier, being prepared for a potential issue is a huge advantage, and that's why checking the tech log is so crucial. But that actually brings us to who these two pilots were. The captain was a 31-year-old Indian citizen with a total experience of just over 6,000 hours. Of these, he had flown 5,176 hours on the 737 family, and the report didn't specify how many of those were flown on the MAX variant, but it couldn't have been many, because it was really almost brand new. His training record was generally good, but he had received some remarks regarding his use of crew resource management on a couple of occasions, as well as some feedback on how he had handled a stall exercise back in 2015. But the problem though was that on this particular day he wasn't feeling very well at all. During the pre-flight he told his first officer that he had the flu, and he could also be heard coughing quite a few times in the cockpit voice recorder. His first officer was a 41-year-old Indonesian national with 5,174 hours of total experience, of which 4,286 had been flown on the Boeing 737. His training record was a lot more checkered, and he had actually failed at least one check early on in his career. That had then been followed up by several checks with very marginal performance, mainly around handling skills, workload management and knowledge of checklists. In fact, the record shows that he had been struggling on almost every check he had done all the way up until this flight. Anyway, the cockpit preparation continued in a normal way, with all briefings being performed and checklists completed. They were clear to follow the Abasa 1 Charlie departure, which would take them straight ahead of the departure until reaching 3,000 feet, where they would turn left via the RNAV points Bunga, Rati and Laras out over the Java Sea. The performance was then calculated with a pitch trim set to 6.6 units for takeoff, a completely normal value for the weight distribution they had, and that trim setting is good to remember. The aircraft eventually asked for push and start, and at time 06:15 local time, the pilots completed the before taxi checklist, set flaps 5, and then asked the Jakarta ground controller for taxi. They were then told to taxi towards the holding point for runway 25 left, and also asked to switch over to the Jakarta tower frequency. All normal procedures and checklists were completed as per standard operating procedures, and at this point there were no fault indications, warnings or flags indicated in the cockpit, but that would soon change. When the first officer called up, the tower controller instructed the flight to line up and wait runway 25 left. The first officer read this back and then instructed the cabin crew to take their seats for departure and started completing the before takeoff checklist. Everything was now ready to go. So at time 06:20 and 1 second, the tower controller cleared Lion Air Flight 610 for takeoff. The captain moved the thrust lever forward to 40% N1, and the first officer called out "stabilized." Toga was then pressed, causing the outer throttle to move the thrust levers into the takeoff thrust position, and the aircraft started accelerating down the runway. A few seconds later, the first officer called out 80 knots, to which the captain responded, "Check." But already here, a small discrepancy in the speed of 79 knots on the captain's display and 81 on the first officer's had started to creep in. Now, that would have been way too small for anyone to notice, but since the angle of attack vanes now also had enough air flowing around them to start working, they were already indicating vastly different values, with the captain's showing an angle of attack 21 degrees higher than the first officer's. Now, like I said before, there was no way for the pilots to see that, but there was one thing that could have given them a clue. You see, the flight directors, those magenta vertical and horizontal lines on the pilot's primary flight displays, were supposed to show a 10-degree pitch down until the aircraft reached a speed of 60 knots, and then they should switch to a 15-degree pitch up. But in this case, only the first officers was showing a pitch up. The captain only moved to a 1-degree pitch down instead, showing a clear split. But at this point, the captain would have focused outside and the first officer on his own displays, so no one would have likely picked this up, nor understand what it meant if they had. A few seconds later, the aircraft called out its automatic V1, followed by the first officer's rotate. The captain started pulling back on his yoke, and as soon as the nose gear left the ground, the underspeed barber's poles shut up on the captain's speed display. This meant that as soon as the aircraft got airborne, the left stick shaker immediately activated, exactly like it had done on the previous flight. And that was also combined with a momentary activation of the takeoff config warning, which the first officer called out. Now remember that this crew likely had no idea about those previous problems, so these sudden, very oral and tactile warnings would have come as a complete startle for them. The captain continued to rotate, but only a few seconds later he called out, "What's wrong?" with the first officer responding, "Autobrake disarm and indicated airspeed disagree." He also called out, "Positive rate," which prompted the captain to ask for the gear to be retracted. And once that was done, the first officer immediately asked the captain if he wanted to return, but the captain didn't answer. So just to clarify, what had now happened was that the left angle of attack vane had once again started indicating a very high 21-degree angle of attack to the left air data inertial reference unit. The angle of attack, like I mentioned earlier, is a measurement of the angle between the wing's mean chord line and the oncoming air, and if that's too high, it means that the aircraft is about to stall. So, since that's what the faulty vane was now saying, the ADIRU and the stall management yaw damper computer immediately activated the stick shaker on the captain's side. That indication was then also sent to make corrections to the speed and altitude on the captain's side, leading to the IAS disagree and soon also altitude disagree warnings. And last but certainly not least, this now also meant that MCAS was primed and ready to start trimming forward as soon as the programmed conditions were correct for activation. But these two pilots would have had no idea of this. For them, this was just a sudden chaos of different warnings as well as tactile and oral stimuli. And in situations like this, it's super important to fall back onto first, the golden rule of aviation: aviate, navigate, communicate, meaning for the captain to just keep pitching to a known value, verifying his trust and then just concentrating on flying. And secondly, for the training of failure management to kick in, which normally says no actions below 400 feet except to cancel any warnings and raise the landing gear with a positive rate of climb. Above 400 feet, providing that the aircraft is under control, the pilot flying should call for the pilot monitoring to help identifying the failure in order for the correct memory items to be performed. But in this case, we are already seeing a deviation from these norms, with the captain asking for identification immediately after rotation and the first officer asking if they should return before that decision could possibly be made. This is a stark contrast to how the previous crew had handled this same problem, and it was soon about to get way worse. About 30 seconds into the flight, the tower controller called the aircraft up and asked them to switch over to the Jakarta director frequency. The first officer read this back without saying anything about the problems that they were having. Instead, a few seconds later, he also called out "altitude disagree," which the captain acknowledged. And you could clearly hear that the tone of the captain's voice indicated some quite high stress here, which I completely understand. The first officer now also called a new frequency up, where the controller greeted them, told them that they had radar contact and instructed them to continue their climb to flight level 270. The first officer read this back and asked the controller if he could tell them what altitudes that they were indicating on his screen. The controller answered 900 feet, which was a value in between what the captain and the first officer's altitudes were showing. But what is important to understand here is that the values shown to the controller is coming directly from the aircraft's own transponder. So if the first officer was trying to figure out which altimeter was working here, he would only get the value corresponding to whatever altimeter was sending its values through the controller, in this case, likely the captain's. This is a very common misconception among pilots, that the controllers are using some kind of raw radar to get accurate values, when in reality they are not. Anyway, the aircraft continued its climb, and after the first officer had completed his call with the controller, the captain asked him to start completing the airspeed unreliable memory items. This was the correct thing to do, and memory items, meaning checklist items that has to be done by memory because of their time-critical nature, are something that all pilots have to know by heart. But the first officer just didn't respond to the captain's request here, and the captain didn't follow it up. Remember, this first officer had struggled with checklist reading and knowledge before, so it is entirely possible that he just didn't know these memory items. Instead, 7 seconds later, he asked the captain what altitude he would like and suggested that they should start flying downwind for the return. Again, this is a sign of the bias from the first officer to just return back and land instead of first dealing with the problem, and therefore the request was also rejected by the captain, who just told him to ask the controller for holding instead. The first officer complied, and as a response to that, the controller asked what the problem was. Now, this would have been a perfect time to declare an emergency, mayday, or at least an urgency, pan, but the first officer didn't do that. Instead, he just responded, flight control problems. And that would turn out to be a big mistake. You see, the controllers in Jakarta had not been instructed to give any kind of priority to aircraft who were just reporting problems. So this controller now just continued to treat the aircraft like any other traffic in his area, which would mean a lot higher workload for the crew, as you will soon see. In any case, the first officer now asked the captain if he wanted to start retracting the flaps, which the captain agreed would be a good idea. But he didn't then follow that up with asking for the actual retraction. So the first officer had to continue to prompt that, which is another indication of the captain being under quite severe workload here. As this was going on, the first officer also soon called out a field differential pressure warning that had appeared, together with a master caution warning. Again, this was exactly like on the previous flight and also connected to the faulty angle of attack vane outside. It's likely that the captain now wanted to try to get some time to concentrate on figuring out the failure, because at time 06:22 and 14 seconds he asked the first officer to take over the controls. But the first officer just responded, stand by, so the transfer never took place, and again the captain didn't repeat the request. The controller had now noticed that it looked like the flight had started to descend, so he called them up and advised them about this, and he also asked what altitude they wanted. The first officer suggested 6,000 feet, but the captain, who was now pulling to get out of that little descent, told him to ask for 5,000 instead, which the first officer also did. And that was also then followed by the first officer continuing to prompt for flap retraction. They were now at flaps 1, so when the captain asked him to take flaps up, the last condition for MCAS activation was now only seconds away. The controller approved the flight to maintain 5,000 feet and now also told them to turn left heading 050 degrees. When the captain started doing that, he momentarily overbanked to slightly more than 35 degrees, causing a bank angle warning. And almost immediately as soon as that warning started activating, the flaps fully retracted and the trim started moving forward in the nose down direction for 10 seconds, driving the trim setting from 6.1 to 3.8 units. Now, the final report didn't specify if this was MCAS or the normal speed trim system who did this. The speed trim system is also supposed to trim forward in a high angle of attack situation to help the pilots push the nose forward. But in this case, the only thing it did was to make it significantly harder for the captain to maintain his climb attitude. So he now called for the first officer to select flaps 1 again, maybe because he felt that he had more controls before the flaps were retracted. And the first officer complied, which again removed the activation conditions for MCAS. The captain also trimmed back up again to a setting of 4.7 degrees of stabilizer trim in order to remove the stick force that he was now feeling, but this whole segment had already led to a short, rapid descent. That descent, together with the flaps extending, actually stopped the stick shaker since it brought the indicated left angle of attack down to 18 degrees. But that would not last for very long. The descent rate reached 3,200 feet per minute before the captain got the pitch back under control and continued to trim nose up again, whilst he also restarted his climb back up. The underspeed barber's poles on the captain's speed display were now sitting at 285 knots, which of course was a crazy high value for their current attitude and configuration, and since the aircraft now started climbing again, reducing the speed slightly, they soon received an oral
"Airspeed low"
warning. This caused the captain to cry out, memory item, but the first officer still didn't understand what checklist he was supposed to go for, so he just responded, fuel differential already done, auto brake, engine start switches off, what's the memory items here? But to that the captain just responded, check, and when the first officer continued with flight control, he just said, yeah. Now if you think that the communication wasn't working really well here, you would be absolutely right. The stress was definitely getting to the captain, and the first officer seemed utterly confused about what checklist he should prioritize, whilst getting very little help from the captain. Anyway, the first officer kept furiously flipping through pages in the quick reference handbook, and he also asked the controller which speed he saw and what was indicated on the radar. The controller responded that the ground speed was indicating as 322 knots, which would have been pretty close to how fast they were actually flying. If they would have done what the previous crew had done from the very beginning and cross-checked their instruments, they would have seen that the first officers and the standby speeds would have been very close to each other. And with that information, they could have therefore transferred controls and maybe gotten things to slow down a bit. But for now, that wasn't done, and the captain just maintained the controls. The crew now also selected flaps 5, and the captain continued trimming further nose up whilst also climbing back up towards 5,000 feet. And as he did so, the overspeed and underspeed barber's poles merged on his speed display, and the stick shaker reactivated. The first officer spent the next few seconds continuing to flip through various checklists, calling out random titles until the captain finally said, No, airspeed unreliable. The first officer acknowledged this, and as that was going on, the normal speed trim was constantly moving the trim slightly, followed by the captain inputting opposite trim. There were also several altitude alerts happening around the same time as the aircraft was still deviating from its cleared 5,000 feet. But at time 0624 and 27 seconds, the aircraft was almost maintaining 5,000 feet. But even though things now looked like they were about to stabilize, the opposite was actually about to happen. As the first officer continued to look for the airspeed unreliable non-normal checklist, which by the way is one of our most important checklists and is therefore written in bold letters on the very front of the QRH, the flight data recorder started indicating that the flaps were being retracted again. Now this was not called out by the crew, and given how deeply concentrated the first officer was in his checklist searching, I would guess that it was the captain who was retracting them, maybe to try out how the aircraft would be reacting. The maximum speed for flaps 1 and 5 is 250 knots, so maybe he had realized that they were likely flying much faster than that and wanted to see if he could get rid of some of the warnings by retracting them. Who knows? In any case, the controller now came in and instructed the flight to turn left onto 350 degrees whilst maintaining 5,000 feet. The first officer read this back, even though in normal situations where checklists are being read, the pilot flying should take the radio, not the pilot monitoring. In the background, the flaps were now commanded fully up, and as they were traveling, the first officer informed the captain that there is no airspeed unreliable checklist, which I'm guessing frustrated the captain quite a bit. But 5 seconds later, the first officer seemed to have finally found the checklists and started reading through it. And as he was doing that, the flaps finally reached their fully retracted position, and MCAS activated, trimming forward for 2 seconds until the captain interrupted it with a manual trim up command. But do you remember what happened every time that the manual electric trim switch was pushed? Yes, this just reset MCAS, which waited 5 seconds and then started trimming nose down again. This now happened 4 times over the next minute, every time interrupted by the captain trimming it back up to normal values again. Now you might ask why this didn't prompt him to start executing the memory items for a runaway stabilizer like the other captain had done, And in order to understand that, you have to understand that a runaway stabilizer was practiced in the simulators as a continuous stabilizer movement, normally only stopped by the pilots executing the correct memory items. This movement that the captain was now fighting was not continuous. Instead, it behaved just like the speed trim system would, only faster. Remember, the pilot on the previous day had actually written that in his report about the incident, which was likely also the reason why he didn't report the runaway stabilizer. He had believed that what he was experiencing was just an effect of the speed trim system being confused, not an actual runaway stabilizer, and certainly not this completely unknown MCAS system. So this captain was likely thinking something similar, and he also could control it without any major difficulty by just stopping the motion with his trim switch and then trimming back up again. So I can definitely understand why the runaway stabilizer checklist didn't automatically enter into his mind, especially with the level of stress that he was now feeling. The first officer kept reading through the airspeed unreliable checklist, with the captain confirming each step when it was done. But they kept being interrupted by the controller asking them to constantly change their headings. The record shows that the crew wasn't following the heading instructions very closely here, which was likely why the controller kept getting back to them. Again, a pan-pan or a mayday-mayday call would have gotten rid of all of these distractions. At the same time, in the background, MCAS kept activating, and the captain kept stopping it and trimming back up, over and over and over again. Eventually, the first officer started looking through the performance in-flight figures needed to fly with unreliable airspeed, and he also soon dinged for the purser to come forward to the cockpit, but the captain asked her to go and get the engineer who was sitting in the back. The engineer then entered the cockpit, and the captain said, "Look what happened," likely pointing out all of the warnings that he had on his screens as well as the continuous stick shaker. But the engineer, who wasn't even rated on the max, didn't have much value to add. The controller at the same time kept giving the crew new headings, whilst the captain, who was obviously concentrating mainly on keeping the aircraft from pitching down, still wasn't following these headings accurately, and the first officer didn't point out his deviations. The controller soon also noticed that the aircraft appeared to be descending slightly again, so he again told them about this and then asked them to switch over to the arrival frequency. When the first officer did this and informed the new controller of their flight control problems, they were told that they could expect an approach into runway 25 left, and that they needed to turn onto a heading of 070 degrees. And now, the captain took a decision that would have very grave consequences. Because at times 06, 30 and 48 seconds, he handed the controls over to the first officer, but he did so without telling him about the issues he had been having with the trim. Maybe he thought that this would be obvious, or maybe he thought that his colleague had noticed it during the many trim cycles which he had already fought with the aircraft. I don't know. But I do know that this first officer had a training history behind him where several of his instructors had highlighted weaknesses in his handling skills. Anyway, the first officer responded, "I have controls," and when he took over, he immediately started by trimming up for 3 seconds, which was a good sign. During the time that the captain had been flying, he had kept the trim between 4.8 and 6 units, even with MCAS activating. But only seconds after the first officer had taken over, MCAS activated again and now brought the trim forward to 3.4 units, without the first officer stopping it like the captain had. When this happened, the first officer claimed, "Oh, was pulling back hard to maintain wings level." The captain, meanwhile, had taken over the radio and was now asking the rival controller if they could route directly towards a point called Esala due to some weather that he saw in the area, which the controller also approved. The first officer now started trimming back, but only for about 1 second, which again reset MCAS for another activation. The captain was still busy talking to air traffic control, explaining their problems and their inability to maintain a precise altitude. He used the wrong call sign here, Lion Air Flight 650, but that doesn't really mean anything. At time 06, 31 and 15 seconds, MCAS activated again for about 3 seconds, before it was, this time, interrupted by the first officer, who trimmed back up again, but only for 1 second. This meant that the trim setting was now at 2.9 units, and with that, the first officer had to pull back with a force of about 65 pounds, or 30 kilos, in order to keep the aircraft from diving. He started trimming back up again, but only for another 3 seconds, never enough to completely take away the forces that he was feeling. And every time he trimmed, MCAS just reset again. The captain continued to talk to the controller, explaining that they needed a block altitude of 3,000 feet above and below their cleared level, and the controller asked around which altitude, to which the captain responded 5,000, interrupted by a panicked call from the first officer, saying that the plane was flying down. But the captain just responded, "It's okay." He clearly hadn't understood the gravity of what was happening, because MCAS had now activated again, driving the trim down to 1.3 units. This meant that the first officer was now pulling 82 pounds or 37 kilos, and the pitch had fallen to 2 degrees below the horizon, creating a descent rate of around 2,000 feet per minute. But this was still not over. As he continued to pull, the first officer also began trimming up, but again only for 2 seconds, which meant that the trim only went up slightly before MCAS activated again, bringing the trim down to a terrifying 0.3 degrees. The first officer was now pulling with 93 pounds or 42 kilos while calling "fly up", but the aircraft still pitched forward into a descent of over 10,000 feet per minute at an altitude of just 3,200 feet. The first officer desperately trimmed back a final time, but by now you know what that means. As the enhanced ground proximity warning system started calling out
Terrain, terrain, sink rate.
MCAS activated one final time, with the overspeed clacker now sounding in the background.
Pull up.
At time 06:31 and 55 seconds, just under 12 minutes after takeoff, Lion Air Flight 610 crashed straight into the Java Sea, instantly killing all 189 persons on board and smashing the aircraft into pieces. During the following minutes, the controllers tried to get into contact with the aircraft, but obviously with no success. Eventually, the accident alarm was activated together with a large search and rescue effort, who soon found wreckage parts floating on the surface of the sea close to where the latest radar trace had been lost. This accident immediately sent shockwaves throughout the world. How could a brand new aircraft like this just drop from the sky seemingly without any reason? The flight data recorder and the cockpit voice recorder were eventually found, and with that the investigation got on the way, soon delivering the details I have explained in this video. Boeing, from the very start, directed most of the blame towards the pilots and the airline, and as you have just seen, not without reason. But a feeling of unease soon started moving through the pilot community. It was soon made public that this MCAS system existed, something that almost no pilot who was actually operating the aircraft knew about, and this system seemed mysteriously powerful for something that was just supposed to be augmenting the maneuvering characteristics. And a lot of pilots also soon started asking, how could something like that have been allowed to rely on just one single sensor?
A single malfunctioning AOA sensor triggered a powerful anti-stall system called MCAS, which forced the nose of the plane down.
The final report, who would take a few years to complete, came up with an astonishing 89 different findings and 9 contributing factors, including serious problems with the certification, oversight of the 737 MAX development, issues with the maintenance in Lion Air, as well as deficiencies in the crew resource management, procedures and handling by the operating crew. Loads of safety recommendations were issued for basically everyone involved, including Lion Air, Boeing and the FAA, as well as the air traffic controllers in Indonesia, who were told to treat reports of flight control problems more seriously. Boeing were quick to issue a flight crew operations manual bulletin describing the problem and how it was supposed to be rectified. They highlighted that existing procedures using normal trim and the runaway stabilizer non-normal checklist was enough to deal with the problem. And with that, I think most pilots and industry insiders were initially quite happy. This was seen as a mishandled technical issue caused by the fitting of faulty parts, and the suggested ways of dealing with it seemed straightforward. But that was before another accident happened, only a few months later. An accident that would completely change the way that people viewed this accident as well as the Boeing 737 MAX forever. I almost cannot put into words how truly horrible the story that I'm about to tell you is. But I can tell you that I tried a tiny taste of what these pilots went through in the simulator,
and I am using everything that I have.
And it really scared me. This is the story of the second Boeing 737 MAX accident. Stay tuned. On the 29th of October 2018, a horrible accident took place in Indonesia, involving an almost brand new Boeing 737 MAX 8 from Lion Air. The aircraft disappeared from radar only minutes after departure, and the pilots had managed to transmit messages about having flight control problems before suddenly diving nose first into the Java Sea, killing everyone on board. I have just released an hour-long video explaining that crash in detail, and I highly recommend you to watch that one before this to fully appreciate the gravity of the story that I will now tell. During the weeks and months after the accident of Lion Air Flight 610, there was a lot of speculation floating around in the airline world. A fully blown accident investigation normally takes several years to complete, and even the interim report, which covers just a bare basic outline of the accident, can take several months before it's released. This means that the involved parties, the airline, aviation authorities and the aircraft manufacturer, have some room to form a public narrative around the accident with the help of the press, who naturally always wants answers straight away about what could have possibly happened. Boeing, who had back then just released the Boeing 737 MAX to the market, was therefore very proactive during those early weeks. Already on the 6th of November, a week after the accident, Boeing issued a flight crew operations bulletin aimed at clarifying what to do in case the stabilizer trim would suddenly and uncommanded start to trim nose down. It explained that this nose-down trim could be activated by, for example, a malfunctioning angle of attack sensor, and the trimming could then last for as long as 10 seconds. This bulletin was sent out to all airlines who operated the type, and it highlighted in bold that this failure could only happen during manual flight. It then went further and explained that this trim movement could be stopped and reversed using normal electric trim input, and that if the failure who caused the trim persisted, well, then the same thing could not happen again 5 seconds after the last pilot trim input, until the stabilizer trim cutout switches were both moved to cutout as part of the existing memory items for a runaway stabilizer. Now, this bulletin is going to be extremely important for this story, so I want to again draw your attention to the wording in it. An angle of attack failure condition that can occur during manual flight only, and that could be solved using the runaway stabilizer normal checklist. Around the time this bulletin was released, information from the ongoing Lion Air investigation also came into the public domain, and it pointed to several mistakes having been made by the operating crew. It also showed that another crew had managed to land the aircraft safely on the preceding day with exactly the same fault. All of this quickly led to a narrative in the press that the crash had been caused largely by pilot error and poor maintenance, and that it therefore wasn't anything really fundamentally wrong with the 737 MAX design. Basically, the consensus was that if these pilots had just been better trained and had followed the existing non-normal checklist, they would have been able to solve the problem. Obviously, this was a gross simplification of the truth, and actually a perfect example of why speculation at an early stage after an accident can be really harmful. But this narrative likely suited Boeing just fine. Pilot error is an excellent overarching diagnosis, and to be fair to the Boeing team here, this was also what most professional pilots thought at the time, including me. Without understanding all the details of what had actually happened in that cockpit, it did seem strange that the pilots hadn't just executed the runaway stabilizer memory items when the aircraft was clearly trimming forward against their will. And as several articles from that time also pointed out, this was Boeing's initial public position as well. But in the background, a lot of pilots and pilot unions were starting to ask some quite hard questions to Boeing. How came this powerful MCAS system had been included in the aircraft design without being highlighted in the pilot manuals? Now, before I go any further here, I realize that maybe not all of you have seen my video about the first MAX accident, so I will now give a short systems review to make sure that this video makes proper sense. The Boeing 737 MAX had been created as a reaction to Airbus's A320neo family that had been fitted with larger and vastly more efficient engines. But the problem for Boeing was that the 737 sat much lower down, closer to the ground, and was therefore much harder to equip with similar larger engines. Now, some of you might ask, why not make the landing gear just a little bit taller? And that's a good question. In fact, the biggest versions of the MAX actually do have a slightly taller gear, but the technical difficulty in achieving that while still making them fit in the same wheel well bay was extremely high. And on top of that, the Boeing 737 family is also certified with overwing emergency exits without slides, since it's sitting so close to the ground. So it just simply can't be made much higher without some further serious changes to the design. Instead, Boeing's engineers had solved this issue by fitting the larger CFM LEAP 1 Bravo engines more in front and slightly higher up than on the previous version, the 737NG. But that then caused some new problems. It soon turned out that these larger engines with their slightly flattened cowlings could, under certain circumstances, start producing a tiny bit of lift, which would act around the aircraft's pitch axis. So, if it was flown at high angles of attack, this momentum then meant that the MAX wouldn't behave exactly like the old NG had done, and that just wasn't okay. To counteract this, the Boeing engineers had added a software program to the existing speed trim system of the MAX, which would only during those very specific circumstances where the aircraft was flown with a high angle of attack manually and with the flaps up, start trimming the horizontal stabilizer in a nose-down direction for a while. That would counteract the nose-up momentum from the engines and basically simulate the feel of the older 737. Just enough to allow the pilots of that previous variant to fly the MAX without any simulator training. The problem was, though, that during the development of the MAX, Boeing had made several assumptions about how pilots would react to this new system if it would malfunction and start trimming forward erroneously. The engineers had assumed that the pilots would instinctively feel that the aircraft was getting out of trim and therefore react within approximately 3 seconds by pulling back on their yoke to keep the aircraft level. They would then quickly activate opposite trim using their manual trim switches, effectively cancelling out the effect of the Maneuvering Characteristics Augmentation System, MCAS. On top of that, it was also assumed that if the failure that had caused MCAS to activate would still persist, well then the pilots would recognize that the stabilizer was acting strangely and therefore go through the memory items for a runaway stabilizer, which would stop the system from trimming any further. Now, all of this sounded good in theory, and if the pilots indeed did react this way, well, then the threat evaluation of the system would categorize it as major, which wasn't so bad and therefore allowed it to only depend on one single sensor. And that categorization would also mean that Boeing wasn't required to do what's called a fault tree analysis, which is a deeper study of how this particular fault could be combined with other failures and how that could potentially affect the crew. During the MAX development, the authority that MCAS had over the horizontal stabilizer had also been gradually increased based on feedback from Boeing's test pilots. But that fact had not been properly communicated or understood by the FAA, who were actually in charge of the certification. So what this all meant was that this had led to a system that was now very powerful when not handled correctly, and also not known by a majority of the pilots who were operating the aircraft, since it hadn't been included in any of their manuals. On top of that, it also turned out that if MCAS was erroneously activated by a failure in an angle of attack vane, those little wing-looking probes on the side of the aircraft who measure the aircraft's angle against the oncoming air, well then its activation would be combined with a whole host of other failures that could distract the pilots from dealing with MCAS, which basically made the assumption of how pilots would react to the failure null and void. But like I said, no one fully understood this after the Lion Air accident, although some pilots did have some serious questions for Boeing. And one of those was a very senior management pilot in Ethiopian Airlines, another early MAX customer. After having attended a Boeing virtual briefing about MCAS in November of 2018, he sent an email to his Boeing representative with a couple of very relevant questions. And because they are so relevant regarding what was soon about to happen, I will now read them out for you. His first question was, according to the briefing, there was no problem with the MCAS system at the time of the accident except being triggered at the wrong moment during the flight due to a single erroneous angle of attack data. But then, why is the system designed in such a way that it operates depending on a single data source, especially when it's such serious consequences, instead of interrogating data from other angle of attack sensors? He then followed up with, any average skilled pilots experiencing multiple failures, as in this case, would react to the abnormalities depending on their sequence of urgency, starting with the stick shaker. Now, all simulator training so far provided require at the first activation of a stick shaker to react in such a way to curb the impending actual stall. It is, though, obvious that all stall warnings are not true, as was the case with the Lion Air 737 MAX involved in the accident, but once a pilot identified a stick shaker to be a nuisance, the next thing that he would do is the airspeed unreliable memory items, not the runaway stabilizer checklist. Because the airspeed unreliable checklist puts a nuisance stick shaker to be an indication of unreliable airspeed. A pilot just can't be expected to put the trim cutout switches to cutout before dealing with the above procedures unless there is a clear guidance or a quick reference handbook procedure addressing such a scenario. And then finally he said, the third question has to do with the very checklist recommended by the bulletin issued regarding the MCAS system, and that is the runaway stabilizer checklist. This checklist commands the pilot to put the stab trim cutout switches to cutout only if the runaway continues after the autopilot is disconnected, and that is not the case with MCAS. MCAS does not continually trim down, it stops trimming, according to the bulletin, for 5 seconds if the control column trim switches are trimmed in the opposite direction. And that will rule out the attempt to categorize the malfunction as a runaway stabilizer and by implication the use of that checklist. So what is the delineation between an MCAS normal operation and the runaway stabilizer? Now, as you can see, these are all very valid questions from a pilot who was concerned about instructing his colleagues in a correct way. Especially his third question, that highlighted that MCAS did not act like a runaway stabilizer as described in the QRH, was extremely important. So, what do you think Boeing answered him? Well, according to the New York Times at the time, this email sent off a flurry of internal discussions at Boeing about what they could and couldn't say since the Lion Air accident was still under investigation. In the answer that was finally sent back, Boeing completely declined to answer the first 2 questions, citing the ongoing investigation. And in the answer to the third, they basically reiterated the information from the crew bulletin that had already been sent out a couple of weeks earlier, saying that in all phases of manual flight, it is expected that flight crews would use normal trim procedures to trim out undesired control forces. Now, I will leave it up to you to decide if that answer was helpful or not, and we can, of course, never really know if better guidance here would have had any impact on what was soon about to happen, but I can tell you one thing, and that is that the investigators of the final report certainly thought so. Now, I will get to the actual flight very soon, but another thing that I haven't talked about much was the type of training that was offered to the pilots who were going to fly the MAX. A big part of Boeing's commercial strategy around this new variant was that existing 737 customers were supposed to be able to transition their pilots onto the MAX without any simulator training at all. You see, scheduling pilots for simulator training, even if it's just for a few hours, is a logistical nightmare that requires taking them off the roster, transporting them to a simulator center, and sometimes also provide hotels and meals for them. And since the Airbus pilots could just go straight into the Neo family after having just some theoretical training, this was what Boeing's commercial department now wanted to do with the MAX as well. Several internal Boeing emails shows that this strategy was considered super important, So important, it seems, that it superseded some airlines' direct requests to provide simulator training for their pilots, as that could create dangerous precedents for other airlines and aviation authorities to follow. This meant that the original difference training that the pilots received only included a few hours of self-study using computer-based training, CBT, basically a few hours on an iPad, where MCAS and its functions was not even mentioned. But at least Boeing had released that flight crew operational bulletin back in November of 2018, so now everyone operating the MAX knew about these possible trim problems, and that the runaway stabilizer memory items together with some easy opposite trimming would solve the problem. Right? Well, this brings us to Addis Ababa Bole International Airport in Ethiopia in the morning of the 10th of March 2019. This was shaping up to be a very nice day, with only some few clouds, light northeasterly winds and a temperature of about 13 degrees Celsius. The pilots who were scheduled to operate Ethiopian Airlines Flight 302 arrived at the airport well in advance and started going through the pre-flight paperwork just like on any other day. The flight was going to take them down towards Nairobi in Kenya, and apart from the 2 pilots, there were also 5 cabin crew and 1 in-flight safety officer scheduled for it. The weather and NOTAMs along the route looked fine, so after having requested the final fuel, the pilots did what they always did. They walked over to the cabin crew and briefed them about what they could expect from the day, as well as any special requests that they might have. In charge of the flight was a 29-year-old captain, who at the time was actually the youngest captain in the airline. Despite his age, he had accumulated over 8,100 hours of total time, of which little more than 4,000 had been flown on the 737NG, as well as 103 hours on the MAX. His training record was very good, with only nice feedback from his trainers and colleagues. A stellar pilot, in other words, which was likely how he had managed to become a captain at such a relatively young age. Together with him was a 25-year-old first officer, but he was significantly less experienced. He had graduated from Ethiopian Airlines' own training academy during the previous year and had only been released to fly on the line in December of 2018, 3 months before the flight. That meant that he only had a little over 360 hours of total experience, with the vast majority of those, 207 hours, having been flown on the MAX, and all of those hours within the previous 90 days. Now, I know that some of my American audience will balk at that low experience, but this is actually quite common in Europe and Africa, especially if the pilots have been brought up through the airline's own approved flight training programs. The first officer's training history also indicated that he had been doing well so far, with no adverse training comments noted at all. Now, we know that both of these pilots had read the Boeing bulletin that had been issued after the Lion Air crash, and we know that because Ethiopian Airlines had sent out the bulletin to all of their pilots and had then been able to track that everyone had read it through their IT systems. You see, Ethiopian was, and still is, a highly advanced and well-regarded airline with a good safety rating and great reputation for their crew training, maintenance and overall quality, which is something that email that I showed you before from one of their management pilots also seems to confirm. This is actually good to remember, as it goes against some of the rhetoric that was floating around during the time concerning the involved airlines. Anyway, when the briefing was complete, the crew all walked together out towards the aircraft that was waiting for them out on the apron. It was an almost brand new Boeing 737 MAX 8, which on this day had only been flying for about 4 months, meaning that it only had 1,330 hours on the airframe. It had no outstanding technical issues with it, except that the captain's iPad charger outlet wasn't working properly. But as it turns out, its first 4 months had not been without issues. Back in December, some pilots had reported that they had observed temporary erratic fluctuations of their altitude and vertical speed indications, and that the aircraft had also started rolling for no reason when the autopilot was engaged. This had then been investigated thoroughly by Ethiopian's engineering department, but since these had been temporary and transient issues, it was unclear if they had been able to completely rectify the faults. In any case, those problems had not reappeared, but other issues like that problem with the power outlet on the captain's side, as well as a starter problem with the APU, had appeared only 3 days before the flight. Now, except for the iPad charger. These had then all been fixed, but it showed that maybe this aircraft had some electrical gremlins still lurking around after its delivery. In any case, none of the pilots who had actually operated the aircraft during the previous day had experienced any issues, so the tech log was therefore reasonably clean. As the crew were boarding, the pilots decided that the captain was going to be operating as pilot flying for the first flight of the day, and the first officer was therefore going to be pilot monitoring. So the captain started by checking out the tech log and then started setting up the aircraft, whilst the first officer went outside to complete the walk around. We don't know much about the pre-flight, except that once the 149 passengers had boarded, there were a total of 157 people on board, and the aircraft's weight and balance was well within limits. On top of that, the pilots had also calculated that the trim setting for takeoff should be 5.6 units, which would be important, and had also decided to use full takeoff thrust with flaps 5 selected. The reason they needed full thrust was because Addis Ababa airport is situated quite high up, at an altitude of 7,656 feet. And the higher up you are, the less thrust the engines will be able to produce, so in this case they needed all of the thrust that they could get out of them. Anyway, the cockpit voice recorder transcript from the final report didn't include the pre-flight setup, so we don't know exactly what was said, but as it turns out, that won't really matter for this story anyway. What we do know is that around time 08:25 local time, everything was ready for push and start, so the first officer called up the ground controller and received clearance to proceed. The two Leap 1 Bravo engines were then started normally, and soon the aircraft was taxiing out towards the holding point for runway 07 right. The before takeoff checklist was then executed as per standard operating procedures, and at time 08:36 and 12 seconds, the pilots received clearance from Addis Ababa Tower to line up and wait on runway 07 right. At this point, there were no warnings recorded in the cockpit and nothing looked out of the ordinary. But that was soon about to change. Now, before we get into the takeoff sequence, I just want to take a few minutes here to explain a few things about the autothrottle system and the way that it normally works during takeoff. We pilots first typically arm the autothrottle when we are clear to line up on the runway as part of the before takeoff checklist. And once the master switch is armed, it will be ready for when the pilot flying pushes the toga buttons, which will then activate the autothrottle servos and drive the thrust up into the takeoff N1 setting. The pilot monitoring will then verify that this setting is correct and normally also call that out, so that both pilots are aware that the system is working normally. As the speed then accelerates past 84 knots, the autothrottle will go into a mode known as throttle hold, which disengages the servos and just keeps the thrust levels where they are. The pilots can still move them manually, but this mode is there to make sure that no sudden retard failure happens during that critical phase of the takeoff. The autothrottle will then keep this mode until the aircraft passes 800 feet climbing, where it will switch over to a mode called ARM instead, which is very similar to throttle hold, except that system will now also provide underspeed protection, which might add thrust if a low speed situation is sensed. But if not, the thrust just stays where it is. The next thing that is supposed to happen is an automatic thrust reduction back to climb thrust, and the altitude for that can be selected manually by the pilots, but it normally kicks in when the aircraft reaches 1,500 feet above the airport level, as sensed from the captain's altimeter. During all normal operations, the autothrottle always handles the thrust for the pilots during the takeoff, meaning that the pilots won't normally have to interfere with the thrust levels much during that phase, and that's worth keeping in mind. Now, while we're on the subject of automatic systems, I should also mention a protection system in the autopilot known as minimum speed reversion. During climb and descent in most vertical modes, this system will cause the autopilot to revert back to level change if the speed drops to less than 1.3 times the calculated stall speed. Level change will then pitch the nose down to maintain that minimum speed, and that stall speed is calculated with the help of the angle of attack vanes. So that, finally, brings us back to the start of runway 07 right in Addis Ababa. At time 08:37 and 14 seconds, the aircraft had fully lined up and the first officer reported to the tower that they were ready for departure. The tower told them to temporarily stand by, but 12 seconds later, Flight 302 were cleared for takeoff and also to follow the Shala 2 Alpha departure as previously cleared. The first officer read this back at the same time as the captain moved the thrust levels up to 40% N1 and then called stable. He then pushed the toga buttons, which caused the engines to roar into takeoff thrust, and the first officer responded, "Check, N1, toga," whilst the aircraft started accelerating down the runway. As the takeoff continued, the first officer verified that the thrust was properly set and then called this out, which was cross-checked by the captain. Everything normal so far. When the aircraft accelerated past 80 knots, the first officer called this out together with throttle hold, indicating that the auto throttle system was now working exactly as expected, and 18 seconds later, the automatic V1 call could be heard, followed by the first officer calling rotate, and 8 seconds later, positive rate, indicating that the aircraft was now airborne and that the gear could be safely retracted. The captain therefore called for gear up, which the first officer acknowledged, and moved the tiny gear level up. But this was about as far as they got using normal procedures. Because on the left-hand side of the aircraft, something had now happened. We don't know exactly what. Maybe it was a bird strike, or maybe it was just a sudden fault that occurred in the wiring of the captain's angle of attack sensor. But we do know that as the gear came up, the master caution light suddenly illuminated, showing anti-ice on the first officer's panel and a left alpha vane on the overhead panel. But the first officer only had time to call out "Master caution, anti-ice" before the pandemonium really started. You see, whatever had caused the heating element in the left angle of attack vane to malfunction had now also affected the values that this vane was transmitting into the aircraft's left air data module and air data inertial reference unit. Initially, that indication decreased slightly before suddenly going violently up to a value of 74.5 degrees, which was to be compared to the 15.3 degrees of the right angle of attack vane. The left ADIRU immediately interpreted this as a massive increase of the angle of attack and therefore a potential stall. The red and black Barber's poles therefore shut up on the captain's primary flight display, and the stick shaker also activated, causing a huge noise in the cockpit and an immediate startle effect for the pilots. Because of these faulty signals from the left vane, the left ADIRU now also started correcting the speed and altitude on the captain's display, which were now showing lower values than those on the first officer's side. Now that should have led to altitude and IAS disagree warnings on the pilot's displays, but curiously those warnings were not sensed on the flight data recorder, nor were they ever called out by the crew. It is possible that these warnings did appear, but that they just were missed by the pilots who were busy checking the master caution. You see, we humans are quite good at registering changes in front of us, like a warning popping up on a screen, but we're much worse at noticing a change to a scene that has happened while we were looking somewhere else. That's why most of you didn't notice that the background lighting here in my office has now switched from white to blue, or that my cup is different. In any case, the captain now, likely in response to the stick shaker, lowered his pitch from the standard 15 degrees to around 8 degrees instead, and he also trimmed the aircraft out for this new attitude. Now, the immediate response to a stall warning should be to execute the approach to stall escape maneuver, but given the fact that the stick shaker only activated on the left-hand side and that his indicated speed was fine for the attitude that he was now flying, even though it was inside of the Barber's poles, this response by the captain to just pitch down slightly would have been fully logical. The corrupted angle of attack values now also started affecting the flight director system, whose pitch bars now temporarily disappeared out of view. They would then come back and disappear several times over the coming few minutes. Now, according to the Ethiopian standard operating procedures, the autopilot could be engaged as early as 400 feet above ground, but that should obviously not be done if a stall could be suspected. But even though the stick shaker was still active here, the captain now twice tried to engage the autopilot whilst calling out "Command!" But in response, he only got the disconnect warning, possibly because he was still inputting a bit of force on his controls, and he also soon called out "What's going on?" in frustration. So why was he so desperately trying to get the autopilot in here? Well, we can't know for sure. Maybe he just wanted to reduce the workload and get a better overview of the situation, but there is also a possibility that he had recognized the signs of an angle of attack malfunction. And do you remember what the recent Boeing bulletin had said about that? Yes, the wording was Boeing would like to call attention to an angle of attack failure condition that can occur during manual flight only, written in bold. So there is a small chance that he thought that engaging the autopilot could potentially solve the problem. This is why it's so important to formulate these type of documents carefully. Anyway, as the aircraft continued climbing through 400 feet, the flight director suddenly came back again and both the LNAV and VNAV buttons illuminated. The captain continued flying manually, keeping the aircraft in trim using his electric trim switches, and he now asked the first officer to contact the controller, which the first officer also did. He reported that they were following the Shala 2 Alpha departure, crossing 8,400 feet. Remember, that's only 750 feet above ground, and that they were climbing to flight level 320. But they didn't yet mention anything about the problems that they were experiencing. The indicated altitude on the first officer's side was indeed 8,400 feet here, but on the captain's side it was indicating about 400 feet lower. Remember, that's the altitude that the auto throttle system was taking its cues from. Someone, likely the captain, now selected heading select instead of LNAV as a roll mode, with the runway heading of 072 degrees still set in the MCP. This is consistent with most failure management techniques, which includes flying straight ahead in case of a major malfunction rather than following the standard instrument departure. Doing that should hopefully reduce workload significantly and help the pilots focus on aviating, navigating and communicating, which are the only really important things in situations like this. The auto throttle engaged in arm as the captain's altimeter climbed through 800 feet as per design, and when they passed 1,000 feet, the captain finally managed to engage the autopilot, which started following the heading selected as well as VNAV in pitch. But that didn't last for very long. Remember what I told you about the minimum speed reversions and how the autopilot would react if an impending stall was sensed? Well, since the left angle of attack vane was now feeding faulty values into the stall management yaw damper computer, it thought that the left speed was way too low and computed that a safe speed would therefore be much higher, somewhere above the barber's poles. This caused the autopilot to now revert to level change and start pitching down in order to quickly achieve this clearly faulty higher speed, and that also meant that the autopilot started trimming forward. This part is very different than what had happened on the Lion Air flight, but it was all caused by exactly the same type of fault. And if you saw that video, you also now know that this was about to get way worse. At times 08:39 and 30 seconds, the radar controller identified flight 302 on his radar and told them to climb to flight level 340 and to turn right to Rudolph when able. The first officer read this back, and as that was going on, there were several small roll and heading oscillations indicated on the flight data recorder. This was likely because the yaw damper had now also been affected by the faulty vane, which resulted in smaller yaw damper activations as per design close to a stall. But it's not sure that this was noticed by the crew, who definitely had more pressing things to worry about. At this point, they still hadn't mentioned anything about any IS or altitude disagree, and the flight data recorder also still didn't indicate that these warnings were actually displayed. But in any case, a stick shaker activation on one side together with a crazy barber pole indication on the captain's PFD could definitely be interpreted as flight with unreliable airspeed. But this was never verbalized, and I kind of understand why. You see, the captain now found himself in a situation where he needed to try and make sense of a stick shaker, possible unreliable airspeed, and an autopilot who wasn't behaving as it was supposed to. Everything at the same time and still during the very early takeoff phase. This was exactly the kind of situation where that guidance on how to prioritize multiple failures caused by a faulty angle of attack vane would have come in very handy. But as I'm sure you remember, that had not been provided. In any case, the captain now pressed level change and selected 238 knots on the mode control panel. Since the speed had already accelerated above the minimum retraction speeds, he now also asked the first officer to start retracting the flaps, which he also did. And the captain then started turning the heading bog towards the right onto a heading of 197 degrees, probably to try and follow the clearance that they had just been given. But he then seemed to change his mind. he asked the first officer to tell the controller that they were unable and to request if they could instead continue on runway heading. Again, a very smart thing to do. But the first officer didn't immediately respond to that request. Maybe because of the high noise level caused by the stick shaker and the quickly increasing airspeed. We don't know. Instead, about 4 seconds later, the autopilot suddenly disconnected. So why did that happen then? Well, the autopilot continuously runs a self-diagnosis, and if the command is for it to climb, but it doesn't do that for a certain amount of time, well then it will just disconnect itself. And since it was still sensing an incorrect low speed situation, it had once again gone into a speed reversion, trying to gain more speed, and had therefore stopped climbing. During this phase, the aircraft reached an altitude of 9,100 feet, or about 1,450 feet above ground, and they now slowly started descending, with the flaps retracted and takeoff thrust still set, but at the same time the left stick shaker was also still rattling away and the speed was increasing rapidly. Because of the low speed reversion, the autopilot had also trimmed the nose down to about 4.6 units before it disengaged, so when the captain now had to take back manual control again, the nose would have already been quite heavy. And now, since the aircraft was flown manually with flaps up and with a sensed high angle of attack, all of the engagement criteria for MCAS had also been fulfilled. So the trim suddenly started running forward at high speed for the next 9 seconds. And as that was happening, the captain was busy with again asking the first officer to request to maintain runway heading and to tell the controller that they had flight control problems. When he finished that sentence, the first ground proximity warning system activation came, calling out "Don't sink," as it felt that the aircraft was now descending during the departure sequence. The first officer now finally did as he was told and called up the controller, telling him that they were unable to continue on the departure. The captain then reminded him to also ask for runway heading, which he did. Ahead of both pilots on their primary flight display, a red pull-up message now also appeared, connected to the GPWS "Don't Sink" oral warning. So you can maybe see now how the situation was getting more and more overwhelming and confusing for the pilots. Since MCAS was allowed to run this first activation to its full extent, it finished with a stabilizer setting of 2.1 units, which is a super low setting. The captain was still holding the nose just barely above the horizon, but to do that he needed to pull with a force of 90 pounds or about 41 kilos. This would have taken his full two-hand effort, and he now started trimming back to try and reduce the force, but he only did so for about 2 seconds. Now here it's probably worth mentioning another feature of MCAS that I haven't pointed out before. You see, because it had been implemented to quickly input trim in order to augment the stick force, MCAS ran the trim at a very high speed, the same speed as the manual electric trim would move with it if the flaps was extended. But since the flaps were now retracted, the manual trim speed had reduced to a much slower pace, which meant that when the captain now trimmed in the other direction, it didn't move the trim nearly as much as MCAS had. On top of that, MCAS had been allowed to activate for 9 full seconds, whilst the captain only held his switch down for about 2 seconds. What this all meant was that when the captain released his trim switch, the trim setting had only risen to about 2.3 units, which was nearly no change at all. But because he had activated the trim, MCAS had now been reset and was therefore ready to activate again. So why didn't the captain stop MCAS when it started, and why didn't he trim all the way back as Boeing had predicted that the pilots would do when they designed the system? Well, we can obviously never know that for sure, but you have to understand the situation that these two pilots now found themselves in here. When Boeing had designed this system, they had assumed a pilot reaction within 3 seconds, but that was when no other problems were present. This crew had a continuous stick shaker, erroneous and differing speed and altitude information, an autopilot that had just disconnected by itself in an already mistrimmed situation, and GPWS activation, all at the same time. It is likely that the startle of the autopilot disengaging with the aircraft descending caused the captain to lose a few seconds as he took over the controls. And MCAS was then continuously trimming forward already, so his immediate reaction would have been to try and hold against the pitch down and to find an equilibrium. And whilst doing that, he simply just didn't trim. The force that he then had to input obviously kept getting worse and increasing as the trim changed, so finding the correct pitch would have been exceedingly hard, and he would have never felt these kind of forces in the controls before, not even in the simulator. Now, the fact that he didn't trim back more once he started is harder to explain, but maybe he felt like it wasn't doing much and instead tried to come up with a more permanent solution. The controller now came back and approved them to continue straight ahead, whilst the captain called out "flaps up speed" at the same time as MCAS activated again, still with the GPWS system calling out "don't sink" in the background. The captain now managed with all of his strength to keep the pitch above the horizon and even to climb a bit, which meant that the aircraft actually managed to reach 1,500 feet above the ground. And if you remember, this is where the auto throttle should have reduced back to climb thrust, but because the faulty angle of attack vane was still sending crazy signals, the captain's altitude now read almost 1,000 feet lower. So the auto throttle just stayed in arm with takeoff thrust still set. Their speed was now around 332 knots, still increasing and also still indicating a stall on the left-hand side. The aircraft had a pitch of around 2.5 degrees and was also still rolling softly from side to side when the crew finally came up with a plan to solve the situation. The captain first called for the first officer to help him trim with me, and he also activated the manual electric trim, which now stopped the second MCAS activation. This was then followed by a manual trim up for about 9 full seconds, but because the manual trim was so slow, it only got the trim setting back to where they had started, at 2.3 units. The first officer now suggested stab trim cutout, which formed part of the runaway stabilizer memory items and was the guidance that Boeing had provided in order to solve the situation. The captain responded in a strained voice, "Yes, do it!" and the first officer immediately did. This meant that the trim wheels now finally stopped moving, but it didn't actually help the situation that they were already in. The trim setting was now way too low, and the captain was still pulling with over 90 pounds just to keep the nose above the horizon. Now, activating the stabilizer trim cutout switches did indeed stop MCAS. The flight data recorder sensed an MCAS activation at this time without the trim moving, but it also removed the pilot's primary way of trimming away the horrible force that the captain was still fighting. According to the runaway stabilizer non-normal checklist, the aircraft can be trimmed manually using the manual trim handles on the trim wheels, but we will soon see that this came with its own unique problems. From time 0840 and 44 seconds, the captain called for the first officer to help him pull up, which the first officer also did, and he also asked him to call the controller and advise him of their flight control problems and to ask if they could maintain 14,000 feet for now, as they were trying to solve their issues. The controller quickly approved this and asked for their intentions, but the first officer just told him that they would call him back. Again, the right thing to do here. The flight path during this time was erratic, with the aircraft pitching up with almost 7 degrees when both pilots were pulling on the controls, causing a climb with around 4,400 feet per minute. And then pitching down with about -2 degrees when the first officer did something else, causing a descent with 2,500 feet per minute. 14,000 feet was now set in the mode control panel, and soon after that the overspeed clacker activated, which triggered the captain to call out "speed", which the first officer also read back. The aircraft had now exceeded the maximum certified indicated airspeed of 340 knots, but still none of the pilots reduced the thrust, which can maybe seem a little bit strange. But you have to remember that at this point, both of the pilots were likely pulling with almost their entire full force on the yoke just to try and keep the nose above the horizon. The faster the speed became, the more effective the stabilizer would have been, and the more force would have been needed in order to keep the nose up. And on top of that, bringing the thrust back would have also caused a further pitch down momentum, since the engines were mounted under the wings, and therefore the thrust actually helped keep the nose up. In any case, the captain, now with more and more desperation in his voice, called out, "Trim, is it functional?" And the first officer responded, "It is not working. Should I try manual?" To which the captain burst out, Try it! But here we come to a truly diabolical detail. Like I said before, the stabilizer was now being subjected to truly extreme aerodynamic forces. And in order for the first officer to move it, he would now need to use muscle power to force the trim wheel to turn with the use of trim handles on his and possibly also the captain's trim wheel. This movement would then transfer through cables to the back, where it would start turning the jack screw to activate the stabilizer and move its leading edge downwards. But at the same time, the captain was pulling back on his control column, which deflected the elevators on the back of the stabilizer upwards. This created a huge momentum around the stabilizer's pivot point, holding against the direction that the first officer needed to trim it. So as the first officer now folded out the trim handle and started to pull with all of his might, the trim wheel likely didn't move an inch. It would have seemed like it was completely frozen. This effect was not something that was taught in any simulator, and it wasn't even properly highlighted in the pilot's flight crew training manual. It turns out that there was actually a way to alleviate this issue, referred to as the roller coaster maneuver, where the pilot flying could momentarily release the back pressure on the controls, which would then take away the aerodynamic momentum for a short while, during which trimming would be possible. And the pilot flying would then be able to pull again, only to repeat the maneuver later, hence the roller coaster bit. But this maneuver was only described in the manuals for the older 737-200s and not anywhere else. And in any case, the likelihood of these panicked pilots figuring this out and at an altitude of 1,500 feet above the ground be willing to let the aircraft pitch down was completely out of the question. I actually tried a similar scenario in a 737NG simulator back in 2019, and even though its forces were not calibrated to exactly simulate the same conditions, we had absolutely no chance to move the trim, and I actually had to ask the instructor to freeze the sim before I lost control. It was pretty scary, even in a sim.
Johan, press the red button. Press the red button now.
And on top of all of that, I should also mention that for this crew to be able to fully trim out the forces that they were feeling, the first officer would have needed to turn the trim wheel not just once, but around 40 full rotations, as each trim unit requires around 15 turns. So, faced with what he perceived as a stuck trim wheel, the first officer now called out, "It's not working!" And the captain responded, "Okay, keep with me," likely referring to helping him out with the pitch. He then repeated that phrase several times over. Around here you can clearly hear strained sounds from the pilots as they were fighting to keep the nose up, and the captain reiterated that they needed to get the aircraft up to 14,000 feet. He now told the first officer to ask for vectors back towards the airport, which the first officer also did. The controller responded and asked them to confirm that they wanted to come back and land, and here you can hear the captain calling out, "Stand by, stand by, stand by," in the background. The first officer responded, "Standing by," to the controller, who then gave them a heading of 260 degrees to follow. The first officer then confirmed this and put it into the mode control panel, followed by another request from the captain to help him to keep the nose up. It is very likely that every time that the first officer did anything else than pulling, the nose was now pitching down. A few seconds later, the captain called out, 14,000, okay, what is it? Master caution?" In an apparent attempt to do some troubleshooting here, something that they didn't really have had time to do until this point. Remember, this was only 4 minutes into this flight. The first officer asked, "Master caution," pressed the recall panel, and then continued with, "Master caution, anti-ice," and then the captain filled in with, "Left alpha vane," which the first officer confirmed, showing that this was likely indeed what was causing the problems. In the background, the stick shaker and clacker were both still sounding, together with a very loud sound of air rushing past the windshield at extreme speeds. The troubleshooting didn't go any further than this. Instead, the captain started calling out, "Shall we pitch? Pitch is not enough! Pitch is not enough!" And then he said, "Put them up." What he was referring to here was the stabilizer trim cutout switches, which had been deactivated earlier as part of the runaway stabilizer memory items. So why would he ask for them to be put back up again when they were the only thing stopping MCAS from reactivating? Well, we can't know this for sure, but I think that the answer is as obvious as it is heartbreaking. With the current trim setting that they were experiencing and the speed that they were at, the pilots were simply unable to keep the nose up any longer. And the captain knew that before those switches had been activated, at least his electrical trim had been working. So he likely reasoned that it was worth it to activate them again and then maybe be able to trim out the forces or even get the autopilot engaged. So at times 08:43 and 11 seconds, the switches were moved back up, and this was then almost immediately followed by the autopilot disconnect wailer as the captain unsuccessfully tried to engage it. Seconds later, the trim switch was manually engaged and the trim started moving up 2 very short moments, but that was enough to again reset MCAS. 5 seconds later, the trim wheel started running forward and kept going for a total of 5 seconds, which drove the trim from 2.3 units down to 1. An impossible setting to counteract for these exhausted 2 pilots. The recorded force on the control wheel now temporarily decreased from 100 pounds or 45 kilos back to 75 pounds, and that immediately caused the nose to drop from 0.5 degrees to minus 7.8 degrees and a 5,000 feet per minute descent. The speed was now well over 380 knots, and despite the 2 pilots pulling for their lives with a combined force of 180 pounds or 83 kilos, the nose now just kept dropping further, with the GPWS calling out, "Terrain, terrain, pull up, pull up." The captain could be heard screaming, pitch up, mayday, mayday, mayday," until the very end. The last recording from the flight data recorder indicated a 40-degree nose-down attitude with a speed of 500 knots and a truly terrifying vertical speed of over 33,000 feet per minute. The aircraft eventually crashed at the time 08:43 and 44 seconds, 23 seconds after the last MCAS activation and less than 6 minutes after takeoff. The impact immediately killed all 157 people on board, and it created a crater over 10 meters deep in the Ethiopian farmland a few miles east of Addis Ababa airport. When the controller lost radar contact with the flight and also couldn't reach them on the radio, he soon initiated the emergency protocol, and the location of the crash site was then quickly found. News of this second Boeing 737 MAX crash spread quickly over the world and completely shocked the aviation community. I actually quite vividly remember where I was when I heard that this had happened. Anyway, the investigation soon got underway, and within days of retrieving the flight data and cockpit voice recorders, it became clear to the investigators that the accident was eerily similar to the earlier Lion Air crash, with the difference that in this case the crew had, at least for a while, followed Boeing's bulletin and used the stabilizer trim cutout switches. This caused the Ethiopian authorities on the 11th of March to immediately ground all Boeing 737 MAX aircraft, and that was then followed by the Chinese, Indonesian and European authorities doing the same on the 12th of March, and then the FAA on the 13th, followed quickly by the rest of the world. The final report eventually came with 88 different findings and a whole host of different safety recommendations, but to summarize, the Boeing 737 MAX was found to have been certified with a system that was, and I quote my friend Björn here, like a tiger in a dark room. You could avoid it, but if it attacked you, it could be deadly. The FAA was found to have delegated too much of its responsibility to their ODA representatives, basically Boeing employees that was representatives of the FAA, and had therefore missed the risk that MCAS had posed. Boeing had obviously absolutely not intended for this to happen, but a combination of commercial pressure to get the aircraft to market and actions designed to avoid pilot training at almost any cost had ultimately allowed this system and its potency to slip between the cracks and to end up more powerful than intended, while also reliant on only one single sensor. But here is where we get to the silver lining of this story. Something that I feel have just been completely neglected by all of the press coverage and even by the Netflix documentary who also tried to explain this story. You see, Boeing and the FAA worked tirelessly over the coming 2 years to rectify every single detail of the 737 MAX that the investigations had highlighted. And when the aircraft was eventually released back into commercial service, MCAS was still there, but it had now become constrained into that little cat in a cage that it was always supposed to have been, not the tiger that it had become. It is also now mandatory for all pilots to do simulator training before they are allowed to operate the MAX, and this training includes how to deal with unreliable airspeed, runaway stabilizer, faulty stick shakers, as well as a detailed demonstration of MCAS. Now, my friend Ben and I have actually just created this difference course as an add-on to our virtual 737 course, which I'll link to here below, so check it out if you're curious. An MCAS itself is now also connected to 2 angle of attack vanes and can under any circumstance only activate once, never reset. If it actually has been activated, or if a fault in the system is sensed, it will then remain inoperative for the rest of the flight, and only that fact is clear proof that the MAX itself doesn't really need this system to fly safely. There were also numerous other improvements and upgrades added to the design, including the angle of attack disagree warning that I mentioned in the previous episode, and all in all, the MAX is, because of all of this, now likely one of the most thoroughly checked aircraft in history. Will there be other problems? Maybe, but I have flown this aircraft myself after it was recertified, and I was really impressed with it. And would I travel on it as a passenger now? Absolutely. Boeing also eventually admitted liability, and in 2021 they came to an agreement with the United States Department of Justice to pay around $2.5 billion in fines and compensations to the families of the victims, as well as to their airline customers. This ordeal shook the American aircraft manufacturer to its core, and the ripple effects of these 2 crashes are still affecting Boeing today. Which is something that I'm following closely over on my sister channel, Mentor Now, which you should definitely check out. Now, I hope that these 2 videos have made the story of the Boeing 737 MAX crashes more clear, and if you like the way that I have explained it, then please consider subscribing. You can also support my work and even see my next video before everyone else by joining my Patreon crew using the link here below. It is now possible to gift a membership, which might be a great idea if you know someone who enjoys my channel and might want to join my next Patreon Zoom hangout. Watch these 2 videos next, they're really good, and have an absolutely fantastic day. Bye bye.